It's my pleasure to introduce Issei, and that's how you pronounce his first name. He's actually from Japan, from Hokkaido. And well, I was excited to have him come here to do his master's because I was in Japan a long time ago and I really liked the country. So the topic of his project is word sense disambiguation. And this is something that we are very interested in basically finding out the sense of a word as it is in context. Every word has a number of, not every word, but many words have different senses, and we want to be able to write programs that can figure out the sense of the word from its context. So this has been investigated for many decades. There's a lot of work that has been done on this topic, and it was a bit of a challenge to get a grasp of all the previous work. But the idea behind this project was basically using translations for this purpose that apparently nobody has done before. So the idea, just very briefly, yesterday another student of mine gave an example of the word aurora in English, which I didn't know, but it actually has two different senses. One is the northern lights, aurora, which I knew, but there's also another sense, which is the first light of the day, the morning light, which I didn't know. And these are these two senses that a human would probably be able to figure out which sense is used in a sentence, but it's a very difficult task for a computer program. But if you consider, many of you speak your own native languages like me, if you consider the translation of those two senses, then you'll probably find that each of those two senses has different translations in another language. And this is the idea behind this project. Let's translate the sentence, let's find out what the translation is, and use this as a hint to find out what the sense of the word is. So I've seen the slides of Issei, and this is a very exciting presentation, in my opinion, because we got really good results, state-of-the-art results on this problem. And a big part of this research was basically replicating many different WSD systems, and in order to show that by adding the translation information, we can always improve results of any system. So not proposing a particular system, but showing that we can improve any system with translations. So probably I'm going for too long already, but let me just tell you that Issei has shown really great skills, programming skills and research skills in this project. Obviously I would want him to continue to PhD, but he wants to go to industry, and he's currently looking for a job in Canada, and I really hope that he will be able to find a job in Canada, because otherwise he will take all his skills and all his talent back to Japan. So if there's anybody here today that can help with that, then please talk to us after this seminar. Okay, so that's all I have. Issei.
Okay, thank you so much for the great introduction, Dr. Kondrak. And yeah, I'm Issei, and today I'm going to present our recent work on rewriting translations to improve word sense disambiguation. And this is a joint work with Bradley, Amir, Arnob, and Dr. Liddy, and my supervisor, Dr. Kondrak. And this work is based on our recent 2 submissions. Okay, now let's get started. As we just discussed in the introduction. So we know natural languages. The languages we are using are ambiguous, like the word Aurora just introduced. So we need the task to tackle this problem, and we actually have the task called Word Sense Disambiguation, WSD in short. So WSD is the task to identify the correct sense of a content word in context, given a predefined sense inventory. And sense inventory is a kind of database which emulates possible senses for each word. And a simple dictionary can be used as the sense inventory to perform WSD, as the Cambridge dictionary shown here. So we can view WSD as the task described in this figure here. So our purpose is to disambiguate the sense of the word, let's say bank in this context. And we have a list of senses from a sense inventory. And our task here is to determine the most appropriate sense of the word bank in this context, in this case, the sloping land. And also we can disambiguate all content words in the same sentence. So this kind of task is called all words WSD. So here's our motivation. And although WSD is a monolingual task, it has been conjectured that multilingual information like translations can help WSD following the intuition here. So if we want to disambiguate the word bank in this context, and if we know the geographical sense of the word bank has this set of translations, but instead the financial sense of the word has financial sense of the word bank has the set of translations like them, then if we could precisely determine the translation of the word bank in this context in other language, in this case the Italian translation river, then using those information we can identify the sense of the word bank should be the geographical sense in this case. However, no effective method of reverting translations has been proposed to date. So in this work, we'd like to answer, can we actually use translations to improve WSD? And especially our purpose here is not to build a new WSD system itself, but to introduce a general method of reverting translations, which can improve existing and future WSD systems. So before going to our methods, I'd like to briefly introduce some important resources for WSD. And the first resource is WordNet, which is a predefined sense inventory in English. And most WSD evaluation and data sets are based on the word senses defined in WordNet. And also WordNet has the specific structure called synset, which is a set of words sharing the same sense. So as you can see here, if you search the noun bank in WordNet, you will find a list of senses, and the synset corresponding to the first sense of the noun bank looks like this. So there is the gloss defining the sense for this synset, and there is the usage example, and also there are synonyms which share the same sense with the word bank. So WordNet is not just a simple sense inventory like a simple dictionary. It can be also used as a semantic network, which shows semantic relations among synsets, like hypernym-hyponym relations. And also it contains sense frequency information, which are originally derived from sense annotated corpora. And such information is very useful, and most WSD systems take advantage of it because sense frequency distributions are very skewed. Another important resource is BabelNet, which is a multilingual semantic network constructed by automatically integrating WordNet, Wikipedia, Wiktionary, and other resources using machine translation techniques. And BabelNet covers over 250 languages. And like WordNet, it also has the structure synset. But unlike WordNet synsets, BabelNet synset is a set of translations sharing the same sense as shown in the picture here. So we can view BabelNet synsets as the mappings among translations and senses. We refer it to as sense translation mappings. So there are several approaches try to apply translations for WSD. And the first research is by Resnick and Jaworski, and they analyzed small word samples in multilingual dictionary and found the phenomenon that highly distinct senses can translate differently. However, they didn't actually propose any method or system based on their observations. Then Diab and Resnick proposed a new WSD system based on English words sharing the same translations. However, their system failed to show improvement over the other system, which rely on monolingual information only. More recently, Apidianaki and Gong leveraged sense translation mappings in BabelNet, as I mentioned earlier, as a hard constraint to improve WSD. However, instead of employing an actual WSD system to apply their method, they just applied their simple hard constraint to a very simple baseline. And also, they used manual translations, which are not always available, and use translations from a single language only. In addition to determine the translation of the source focus word in question, they just applied a word alignment tool to a small size of the test data. So it resulting in the poor word alignment accuracy. So due to those problems, when tested in English, their method failed to show improvement over the simple baseline. And when tested in languages other than English, again, it failed to outperform other systems rely on monolingual information only. So as I mentioned earlier, our proposal is to make the method which can be applied to any systems to improve the WSD accuracy. So we actually need the base WSD system to test our method. So in the following few slides, I'd like to introduce those WSD systems we employed in our experiments. But first of all, there are two main approaches for WSD systems, supervised and knowledge-based. And the supervised systems require training data, which is usually sense-annotated corpora. However, such corpora is very hard and expensive to obtain, and they mainly exist for English. So supervised approaches are usually applied for English WSD. And since they use training data, they acquire higher accuracy compared to knowledge-based approaches. On the other hand, knowledge-based systems don't require any training data, but instead they only rely on lexical knowledge base, such as WordNet or BabelNet, so that they can be applied to both English and multilingual WSD, the WSD performed in languages other than English. And due to the lack of training data, of course, they show lower accuracy compared to the supervised systems. And in our experiments, we employ IMS, LMMS, and SVC for supervised systems, and Babelfy UKB and SensEmBERT for knowledge-based systems. So let's start with the first system, IMS, which is a canonical supervised WSD system with SVM using lexical features such as surrounding words, part of speech tags, and local collocations. And we replicate the results reported in Raganat et al. In 2017. They proposed a unified evaluation framework for WSD and reported performance of various existing WSD systems. And also, recent WSD work has been evaluated on their evaluation framework mainly. So instead of focusing on the original paper, we try to focus on the Raganat et al. Work. And we train IMS using SemCore, which is most popular manually created sense annotated corpus in English. And also we test on the standard benchmark datasets, which is originally from SensEval and SemEval shared tasks. And as a result, we could almost perfectly replicate the reported results in R17. And the next system is Babelfy, which is a knowledge-based system applying random walks with restart to BabelNet. However, it doesn't use translations in BabelNet. And we again replicate the results in our 17 paper, and we could get very close F-score in total. And the next system is UKB, which is also a knowledge-based WSD system applying personalized PageRank to WordNet. And the UKB sets the current state-of-the-art results for knowledge-based systems. And we replicate the newest results in their paper, and we could get the exactly the same state-of-the-art results. And before going further to modern WSD systems, I'd like to briefly go over the basics of contextual embeddings, which are shown to be very effective for various NLP tasks. Several years ago, the idea of word embeddings has been introduced as static word embeddings like word2vec or glob. And they produce fixed length vector for each word as shown in this figure here. So given a corpus, we have different occurrences of the same word bank in different contexts. And using those models, we can obtain a single word embedding for the word bank. So this resulting word embedding has the problem that this one single embedding conflates different senses. In this case, the geographical sense, financial sense, and so on. So to address this issue, recently contextual word embeddings like Elmo or BERT has been proposed. And they are hidden state representations from neural language models. And they instead produce fixed length vector for each word in each context. So in a given corpus, we again have different occurrences of the word bank in different contexts. Then each occurrences of the word bank will get different word embedding. So one of the most popular contextual embeddings model is BERT, proposed by Google. And BERT is a pre-trained bidirectional transformer encoders, and BERT shows the state-of-the-art results in various NLP tasks, including WSD as well. And in addition to the standard BERT, which is only for English, they also propose multilingual BERT, which is pre-trained on 104 languages with shared vocabularies so that it can produce contextual embeddings for those 104 languages in the same vector space. So the first system which leverages BERT embeddings for WSD is LMMS. LMMS is supervised sense embeddings using SemCore based on BERT embeddings. And they perform WSD using one nearest neighbor approach as shown in this diagram here. So when testing, we have sense embeddings for each possible sense. And for the test word in the test context, we run BERT again to get the test contextual embedding. And we simply compare each sense embedding with the test embedding to compute the cosine similarity. In the end, we choose the sense with the highest cosine similarity as the final sense prediction. And we take the pre-trained sense embeddings, and also we use BERT model to compute test embeddings by ourselves. As the results, we could replicate the original results reported in their paper. And the next system is SVC, which is also supervised WSD system using ensemble of transformer models. And their model takes BERT embeddings as inputs as well. And also their model is trained not only on SemCore, but also with additional information from WordNet, such as hypernym relations. And their model sets the current state-of-the-art results for supervised systems. And by using their pre-trained model checkpoints, we could replicate their results. So the last system we employ is SensEmBERT, which is a knowledge-based multilingual sense embeddings using multilingual BERT embeddings with BabelNet. And since they are sense embeddings, they also perform WSD using 1-year SemEval approach like LMMS. And their results shows the state of the art in both English nouns and multilingual WSD. So we also take their pre-trained embeddings and use multilingual BERT to compute test embeddings. As the result, we could get very close F-score to the reported results. So far, I've introduced the previous work and introduction. So is there any questions so far? No, maybe then I can move on to our methods. So first, I'd like to introduce our assumption here. So as I mentioned earlier, our proposal here is to propose a method which can be applied to a base WSD system. So we actually need actual WSD system to test our methods on top of that. So we assume a base WSD system performs the WSD formulated as follows. So for a focus word E in context, the base WSD system select the correct sense S from the set of possible sense candidates. And the way how the base WSD system choose the correct sense is that first it will assign numerical value or score like probabilities to each sense. And finally, it takes the sense with the highest score as the prediction. And this kind of architecture is very common for most WSD systems. So we assume our method can be applied to any WSD systems following this architecture. So first, I'd like to introduce our baseline method, HardConstraint, which is an extension of Abidianaki and GOM. So we also take BabelNet sense translation mappings as a hard constraint, and so that we can rule out senses if their corresponding BabelNet synsets do not contain the translation. However, instead of using translations from a single language, we use translations from multiple languages using intersection strategy. So this figure here shows how to constraint with intersection strategy work. So given word children we want to disambiguate in this context, we first translate the entire sentence and perform word alignment to identify the exact translation of the word children in different languages. And then we look up BabelNet synsets to see which sense is mapped to which translation. As a result, we could get the set of senses for which are mapped to each translation. In the end, we simply take the intersection of those sets of senses to get the remaining sense candidates. And in other words, we rule out senses if they are not mapped to all possible translations. So from the remaining sense candidates, we choose the highest score based on the base WSD system to make the final prediction. So in the ideal case, we could get only one sense remaining after the intersection, so it will be the prediction. If we have the empty intersection, then we cannot use translation information correctly, so we just back off to the base prediction. So although hard constraint is simple, it is very inflexible because it can accidentally rule out correct senses due to the noise in translations or BabelNet. Actually, it has been shown that BabelNet contains translations for only 79% of nominal senses in WordNet. And also such translations have an average precision of 72% only. So we need more robust method to handle this kind of noise. So that we propose our principal method, SoftConstraint. And this figure exemplify how SoftConstraint works. And SoftConstraint is composed of 3 different information sources. And the first information came from the base WSD system. It makes the prediction for each sense with some kind of score like probabilities. And then we get the translations and query BabelNet to get some kind of score based on translations. And then we get the sense frequency information from WordNet or other resources as the third component. So based on those three components, SoftConstraint makes the sense prediction based on this formula here. So SoftConstraint compute the weighted products of those three components with tunable weights, alpha, beta, and gamma. And it will assign the resulting score p tilde to each sense, which is the unnormalized measure of probabilities. And as a result, we will choose the sense which maximizes this score as the final sense prediction. So the PWSD is very simple. We simply take the scores assigned by the base WSD system to each sense, and we normalize them to form the probability distribution. And the second component, P-trans, is computed based on the translations for the source focus word in BabelNet. So we compute P-trans based on 3 steps. First, for each translation T, we assign some weight WT computed in this formula. So this formula indicates that WT is computed as the inverse of the number of senses mapped to the given translation T in BabelNet. So this formula represents the discrimination power of the given translation. So if the given translation is mapped to less senses, in other words, if the given translation reduces the senses more, then we assign more weight to the translation. So in this case, the Russian translation DTR will get the highest weight. After that, we compute score for each sense based on the weights we just computed by taking them for each sense, taking the sum for each sense. And in this formula, we assign higher weights for the sense which are mapped to more translations because we consider if the sense is mapped to more translations, that sense should be more appropriate based on the translations. So in this case, sense number 3 will get the highest score. After that, we normalize those scores just computed to form the probability distribution P-trans. And when performing normalization, we also perform additive smoothing to avoid zero value. And the last component, PFREC, is sense frequency information. And for English, it is available in WordNet, which originally takes the information from SemCore, a sense-annotated corpus in English. And since SemCore doesn't cover all possible senses in WordNet, we perform additive smoothing to handle zero frequency. For the languages other than English, since we don't have any high quality sense annotated corpora to induce sense frequency, so instead we apply sense distribution learning SDL method, which is a method to automatically estimate the sense frequency distribution from a raw text corpora. And we employ CuRBERT, which is a state-of-the-art method for unsupervised sense distribution learning. And it applies clustering algorithm to BERT embeddings to perform SDL. And like our methods, CuRBERT is also language independent and it doesn't have any additional training data requirements. Okay, so far I've introduced our methods of reverting translations to form a constraint which can post-process the predictions by the base WSD systems. In addition to that, we would like to introduce another method of reverting translations, which is called TM. in TM method, we leverage translations as contextual embeddings. So instead of post-processing the predictions as the constraint, in TM method, we form a contextual embeddings and use it as the input to a modern WSD system so that we can bias the sense predictions made by the base WSD system itself. So as shown in this diagram here, so the modern WSD system will take the contextual embedding for the test word as the input. So in addition to that, we also induce the translation embedding using some contextual embedding model. And we concatenate those two embeddings to form a new input embedding and feed it to the WSD system and run it as usual. However, this method is less general compared to those post-processing constraints because not all systems are using word embeddings. So we test this method in a part of our experiments only. So I've introduced the method of rebadging translations so far. However, the quality of those methods will highly dependent on the quality of word alignment. Because even if we can properly translate the source sentence into other languages, everything will be useless if our alignment algorithm performs poor, because we need to identify the exact token or translation for the source focus word in question. So to address this issue, we propose a novel knowledge-based bytext alignment called BabAlign. BabAlign combines existing alignment tool with BabelNet, and it comprises 3 steps as follows. First, we perform pre-processing to test data, and we perform lemmatization and part-of-speech tagging. However, usually WSD test dataset is too small to perform a good word alignment. So we also add a pre-processed bytext, large amount of bytext to complement the size of the data. In addition to that, we also add the translation pairs extracted from BabelNet so that we can bias the prediction from the word aligner to make the prediction for alignment links among varied translation pairs appearing in BabelNet. So after we prepare the input data, we employ some existing alignment tool to run the word alignment to get the initial alignment links. After that, we can post-process such initial links using BabelNet to fix wrong and missing alignment links. So here are the general workflow of the post-processing stage. So starting from the initial alignment links, source word S and translation T, we first check if the translation T is actually appearing as the translation for S in BabelNet. If so, we run compound search function to search through the target surrounding words to recover compound. And we can get a new updated alignment link, S and T dash, which contains the original translation T, and also it doesn't violate other alignment links. If the initial alignment link is invalid, we go to the BabelNet search function, which searches target sentence to find the valid BabelNet translation. And if we can find such translation, we just update the alignment link. And if we couldn't, we keep the initial alignment link. So here are the examples for both functions. So if we initially get the alignment links like this, and if we want to identify the precise translation for the word playmate, then we first check if the initial translation companion is actually valid translation or not. By checking BabelNet, it turns out to be a valid translation. So we run compound search to search through the surrounding tokens which are not aligned to other tokens yet. Then we can actually find a compound, companion denoc. So we actually expand the alignment link to the entire compound. On the other hand, if the initial alignment link aligns wrong translation, in this case, sun and tramontare, we look at BabelNet, actually tramontare is not the translation for the word sun. So we perform BabelNet search to search through the target sentence to find the valid translation. In this case, we could actually find the valid BabelNet translation sole. So we deny this initial alignment link and make the new alignment link sole. So that's all for my methods. And now we can move on to our evaluation. So first of all, we'd like to validate our BabAlign algorithm in both intrinsic and extrinsic evaluation. So we perform intrinsic evaluation by evaluating the alignment accuracy on parallel datasets with gold alignment. As the dataset, we take SemCore, a sense-annotated corpus in English, and their manual translations in Italian and Japanese, M.Sc and J.Sc. So from those datasets, we extract about 600 sentence triples with 2,600 aligned tokens, and those tokens share the alignment links among those three languages. And as the additional bytext, we employ open subtitles, which comprises about 37 million sentences for English Italian and about 2 million sentences for English Japanese. And for the source side, which is SemCore in English, we use annotated lemma and part-of-speech information for the pre-processing stage. And the reason for this is that most WSD evaluation datasets contains such information, so we can use that. For the target site, M.Sc or J.Sc, we have two different settings. For unannotated setting, we use morphological taggers instead of the existing information because in the actual WSD setting, we only have the dataset, annotated dataset for the source language we want to test on, and we have to automatically translate the text where we don't have such information. So in the other setting, which is annotated setting, we keep using the annotated information like in the source site. And this setting emulates the ideal setting where we have parallel test datasets for all languages. And as the base word aligner, we employ FastAlign, which is the one of the most popular alignment tools in NLP field. So here are the results. And we evaluate on F-score in terms of whether the aligned translation lemma by the aligner matches the gold lemma in the data. And the blue bars indicates the F-score of FastAlign in different size of dataset. And the BabAlign, the orange bars shows the F-score of BabAlign. And as we expected, by adding the huge amount of data to the test data, we can get a huge gain for the alignment accuracy. And also by adding the additional translation pairs from BabelNet, we can get further gains. It indicates our intuition of biasing what aligner works. And also, BabAlign shows further improvements in both language pairs in both settings. So for English-Italian alignment in annotated setting, there are only 6 instances where BabAlign hurts the correct prediction made by the base system, which is FastAlign. And there are 2 types of such errors, and the first type is caused by BabelNet deficiency. For example, given a sentence pair like this, FastAlign correctly aligns the word get to the proper translation recovery in Italian. However, unfortunately, BabelNet doesn't cover recovery as the valid translation for the word get. So we search through the target sentence and we accidentally find a similar translation essere, which is not aligned to any source tokens. And essere is actually a valid translation for the word get in BabelNet. So our algorithm deny the correct alignment link and make the new alignment link, which is wrong. And the other type of error is caused by annotation error in the dataset itself. For example, the word navy is initially aligned to the Italian translation blue, which means blue in English. And our algorithm expand the alignment link to blue squirrel, which means dark blue, and dark blue should be more appropriate for the translation of navy. However, in multi-semquer M.Sc, the gold alignment shows the alignment between navy and blue itself only. So our new alignment links are improperly treated as the wrong alignment link. So this type of error indicates our potential use of BabAlign as the tokenization error correction for the data. And we also evaluate on the extrinsic evaluation, and we employ the task called cross-lingual lexical entailment defined by Viers and Caput. And they define this task as detecting whether the meaning of a word in one language can be inferred from the meaning of a word in another language. And we take the binary classification setting for this task introduced in SemEval shared task this year. And this task can be viewed as the example here. So given a word pair in different languages, in this case, English and Italian, we predict whether this word pair holds the entailment relation or not. So we test BabelNet in our submission for SemEval shared task this year. And our method is based on one assumption, which is that a line translation pair either represents the same concept or one entails the other. So based on this assumption, we formulate the method in two steps. First, we align the bytext to extract all translation pairs. And then we check if the given test word pair appear in the extracted translation pair. And if so, we determine such test word pair holds the entailment relations. So we test in 4 language pairs from the shared task dataset: German, English, Croatian, Italian, and English, Italian. And each dataset comprises 2,000 to 3,000 pairs. And we also employ one open subtitles as our bytext, and we apply lemmatization and part of speech tagging using those tools. And as the base word aligner, we again employ fast align. So as shown in the example, in the results here, so our results, BabAlign outperforms the fast align in all languages, especially shows the huge gains for those 3 language pairs, which shows the advantage of BabAlign in downstream tasks. So now let's move on to the WSD experiments to test our methods of reverging translations. First of all, we'd like to test in the Oracle setting where we have manual translations and gold alignment. And as the dataset, we use the same dataset used in the intrinsic evaluation for alignment. And we split the test set into 10% and 90% for tuning the weights in the SoftConstraint method. And we employ 2 systems, Babelfy and UKB. And both of them has the variant of using sense frequency information in their system. So the Babelfy full system backs up to WordNet first sense, which simply chooses the sense with the highest frequency in WordNet. And UKB full system uses the full information of sense frequency as the feature denoted as dictionary weight. And when testing on plain system without sense frequency information, we also disable pfreg in SoftConstraint for fair comparison. So here are the results on the test set. As you can see, SoftConstraint shows the substantial improvement over the base system, up to 50% F-score gains. And although HardConstraint can also show the good improvement due to the Oracle setting, SoftConstraint keep outperforming the HardConstraint. And the reason for the modest improvement in Babelfy with WordNet fast sense is that Babelfy backs off to too many instances, about 80% of the test instances with the WordNet fast sense, so precluding our use of translations. We also perform additional experiments, and these results show that by combining Italian and Japanese translations, we can get further improvement compared to using translations from only a single language. So the next set of experiments are English OWASD WSD using standard benchmark datasets with no manual translation. We employ 5 datasets from the evaluation framework, and we test on 2 knowledge-based systems and 3 supervised systems. And since those standard benchmark datasets don't have manual translations, so we have to automatically translate those sentences to get translations. So we employ state-of-the-art neural machine translation models, especially pre-trained English-German, English-French models, and English-Russian models. And as usual, we perform word alignment by using BabAlign after translating the source sentences. And here are the results on the knowledge-based systems, UKB and Babelfy, on the concatenation of all 5 datasets. As you can see, HardConstraint sometimes fail to show improvements due to the noise in translations and BabelNet. But on the other hand, SoftConstraint can keep showing the significant improvement over the base system. And especially by showing the improvement over the state-of-the-art system, UKB with dictionary weight, our SoftConstraint result sets the new state-of-the-art for knowledge-based WSD. And here are the results for supervised WSD. And again, HardConstraint completely failed to show improvements, but SoftConstraint can show good improvements over the strong supervised systems, except for SVC, which we show the same results. The last set of experiments we perform is multilingual WSD. We employ test sets from 2 shared tasks, and we test on German, French, Spanish, and Italian. And since they are parallel test set, we can get manual translations, but we also want to test our methods in the noisy setting where we extract translations from machine translation systems. So we have 2 evaluation settings. For machine translation setting, not all language pairs have pre-trained NMT models. So instead, we employ Google Translate to obtain translations in English. For manual translations, we get translations from all remaining test sets. So in this case, if we test on Italian, we obtain translations from those remaining 4 languages. And also we perform word alignment using BabAlign as usual. And we test in 2 different systems. The first system is IMS trained on OneSec, which is an automatically developed sense-annotated corpora in multiple languages. And the other system is SensEmBERT, which is a state-of-the-art system in multilingual WSD, as I mentioned earlier. And since SensEmBERT uses the embeddings from Multilingual BERT, so we also use Multilingual BERT to test TM method. And for simplicity, we only use English as the target language here. And for the sense frequency, we either disable pfreg in SoftConstraint or use CRUBERT to automatically estimate sense frequency for it. So here are the results using IMS with OneSec. For both Google Translate and manual translation, we can get a great improvement over the base system. And especially SoftConstraint using sense frequency information from CRUBERT shows the best results. And also surprisingly, using Google Translate shows the similar improvement compared to manual translation, which indicates the robustness of our method, especially SoftConstraint. And here are the results for SensEmBERT, which is the state-of-the-art system. We can get similar improvements, and especially by adding translation embeddings, TM, we can get further improvement. And again, by showing substantial improvement over the state-of-the-art system, SensEmBERT, our results set the new state-of-the-art for multilingual WSD. And we also perform an additional experiment using an actual NMT system from Ng et al., which is pre-trained German English state-of-the-art NMT model. And we test on German test set, and we see similar improvements over manual translation, Google Translate, and NMT model. And surprisingly, sometimes an NMT model can slightly improve over the manual translations. Our analysis shows that sometimes neural machine translation prefer the literal translation, which makes our alignment algorithm easier to find the correct translation. So throughout our WSD evaluation, we found that SoftConstraint is beneficial in the following two situations. First, it can effectively use sense translation mappings from BabelNet to correct the wrong predictions, even when HardConstraint couldn't. And also, it can avoid miscorrecting the proper sense predictions made by the base system. However, even SoftConstraint cannot help WSD if all translations are wrong. For example, in the sentence here, the word zip has the sense of energy instead of the sense of fastener, and the base system UKB correctly predicts the sense of energy. However, when we translate this sentence using the NMT models, all NMT models fail to translate the word zip correctly. Every models use the sense of fastener to translate the zip. So this caused the error in our methods, and all of our methods fail to predict the sense of energy. So to wrap up, we propose a robust method to reverse translations, which integrates manual or machine translations with BabelNet. And our primary results, SoftConstraint sets the new state-of-the-art for English and multilingual WSD. And also we introduced a novel word alignment algorithm, BabAlign, which outperforms the existing word alignment tool in both intrinsic and extrinsic evaluation. And as the future work, we'd like to explore more general way to integrate TM so that we can test it with other systems as well. And also we would like to test BabAlign as tokenization error correction as mentioned in the experiment section. So that's all for my presentation. Thank you for your attention. Is there any questions I can take for next few minutes?
Thank you. It's a fascinating talk, lots of interesting material. If I understood it right, you looked at each individual word by itself and tried to find the best interpretation. Are there situations where one word is ambiguous and another word in the same sentence is ambiguous, and the correct resolution is to look at them both at the same time rather than look at each word by itself?
Yes, actually, do you mean the same word occurs twice in the same sentence?
No, I meant I was trying to think of some example of it, but where you have the word bank appears and also the word, I don't know, child appears or something, and there's several interpretations for each word individually. But there's a rather low likelihood word occurs for each one of them, but that makes it consistent. I don't have a good example, but maybe you have some examples.
Yeah, actually, existing WSD test sets contain such kind of instances, and in that case, in the gold annotation, they list multiple sense keys, which all of them can be correct in this context. And our task here is to predict one of them. We don't aim to predict everything. So if we can predict one of the correct sense in that context, then it will be fine.
I meant that again, I don't have a good example, but imagine for word 1, there was 2 senses, and for word 2, there's also 2 senses. And the only one that makes sense is if, if it's the 1-1 combination makes sense, but the 1-2 and the 2-1, the 2-2 don't make sense. But you don't know that until you look downstream for another word.
Sorry, I couldn't really.
I'll ask you later on.
Okay,
So
thanks.
can I make a comment on that?
Sure.
Yeah, so I think for humans to understand a language, there are very little backtracking or dynamic programming in our mind. It's almost greedy. Like when you look around some context words, you almost know the meaning of the back. It's very unlikely that you need to do like a lot of backtracking and then you determine like 9 out of 10 words in a sentence, and you eventually say the last words, you cannot do that. Then I backtrack what it means by the first word. So I think it's almost unlikely.
So they're sort of garden path sentences, the old man, the boats, right? Where, at the end, the old man makes sense, but then you realize that the old man, the boats, the word man had to be the verb.
Yes, so actually, yes. So it's not common in real language.
Yeah, and actually our WSD task is based on not a word, but we focus on word types, which is the word given a part of speech. So we will not confuse like verb with noun. We only focus on like the word given like the usage with part of speech tag, and we just try to find the sense inside that part of speech.
And also, I think Yixing's work tries to make use of the context. So I think it's a like rough estimate of the context, and you can almost detect the sense of a word greedily, or individually. And then I think the current performance of all machine learning models in terms of in language tasks is not great. It's too weak to consider these strange cases like we humans can't understand it very well. Then that's not the main focus of machine learning models.
So to answer my question, it would have a hard time with that situation if it ever occurred, but so do people. Is that the right summary?
Yeah.
So I think it's already 1 p.m. So is there any other questions?
Doesn't look like it.
Okay.
Okay. Just a reminder in case anyone wasn't here when I said it at the beginning, there's still more times available to meet after, or I guess right now. So you can sign up on the Google Sheet. I sent out the link over the chat so you can access it there. Okay, so thanks very much for the presentation.
Thank you.
Thank you.